Number 6. A 120 kilogram box sits on top of a ramp that has a 25-degree incline. If it is pulled at 1,000 newtons towards the top of the ramp, what will be the resulting acceleration? Neglect friction. So in this first problem, you're neglecting friction. In fact, our next problem is actually going to apply friction to this problem. Okay? So let's just take this one step at a time. Let's start by drawing out our picture. Okay. So on this box, we have gravity pulling it straight down. And then we have the components of gravity interacting with this inclined plane. So on the incline, parallel to it, we have a force that we'll call X, which is an effect of gravity. And then perpendicular to it, we have a force we'll call Y, which is part of gravity as well. So this angle right here between Fy and Fg is going to be the same angle as the ramp. Okay? So, using our magnitude, so using our trigonometry, we're going to determine the magnitude of y, the magnitude of x. And this x is going to be what resists that applied force. Okay? So let's go ahead and break these out. Let's run out our variables and then figure them out piece by piece. So first we've got an F net. We almost always have that. And in this case, we're going to have an applied force and an Fx, and that's going to become our F net, those two together. We've got that F1, that applied force. We have our force of gravity. We have our Fx. We have our Fy. What else do we have? That should be it. For this problem, that should be it. So then, let's factor in our mass, our acceleration, I'm not sure if we're supposed to find that, our gravity, and our theta. So our gravity is negative 9.8, our theta is 25 degrees, our mass is 120 kilograms, and our F1 is 1,000 newtons. Okay. Now before we go any further, what I think has been tripping us up so far is that our positives and negatives are working according to the ramp, not our standard coordinate system. It's not this. In order for us to do these calculations properly, we're basically flipping this ramp. So our coordinate system, our x and y, what's going to tell us what's positive and what's negative, it's going to be like this. Okay. So we're doing that right away so we don't end up halfway through the problem and trying to figure out what our positives and negatives are. So let's go ahead and determine. Our F1 is going in the upwards direction, but it's also going to the left. So we're going to say, using this coordinate system, it is negative. Our force of gravity has a negative component and a positive component. The force of gravity itself is going to be negative. However, when we break it out into two separate components, it's going to have a positive one and a negative one. So, for now, we're going to manually remember that that's what that's supposed to be. Later on, we're going to use a coordinate system that will actually tell us when our sine or our cosine is negative or positive, based on where it is on a 4-quadrant coordinate system. That's a little more complexity up front, but it actually saves us a little bit of time on the other side. But for now, we can't handle that extra complexity up front. But we'll get there. So I want you to know that having to figure this out in your head by looking at the paper, it's not going to stay that way. We're going to get better, and then the numbers will work themselves out. But for now, we have to babysit those numbers. Okay? So that Fx, that should be positive. Whatever magnitude I get, it should be positive because it's going in the positive direction. That Fy, that should be negative. No matter what value I get, it should be a negative number. And that Fg is also going to be negative. Okay. Now my F net, I don't know, because if Fx is greater than 1,000, then it's going to pull it this way. And then my F net would be positive. If it's less than 1,000, then my F net is going to be going this way, and it's going to be negative. So I have to figure that one out first. What I do know is my F net is going to be equal my F1 plus my Fx. Okay? And then my F net also equal to ma. And that's where I'm going to find my resulting acceleration. So let's go ahead, find our force of gravity, and then find our components, and that will help us solve the rest of this. We're always going to start by finding our base forces and our components. Force of gravity is 120 times negative 9.8. That's going to give me a negative 1,176. And then to find my force in x and my force in y, I'm going to use trigonometry. So sine of theta is opposite over hypotenuse. And my theta, the theta I'm using, is this angle right here. Well, my x is going to be the opposite side of that angle. So I'm going to use Fg times sine theta is going to equal the force in x. Plugging my numbers in, I've got a negative 1176 times sine of 25 equals what? That's going to give me 496.9. Actually, that's 0.99, so I'm going to say 497. I'll round it up to 497 newtons. And remember, it's got to be positive because it's the force in x. 497 newtons. So then to find my force in y, I'm going to do the same thing, except this time I'm going to use the cosine. Okay, so plugging those numbers in, 1176, cosine 25. And that's going to be a negative, because it's in the y, we already just find that direction has to be negative, 1066 newtons. Okay, so now I see my force in x is 497, my force applied is 1,000 newtons. So my resulting F net is going to be in this direction. So my F net will be negative. Okay, so now let's go ahead and figure out what our F net actually is. So F net is equal to a minus 1,000, a negative 1,000, sorry, plus 497. And that's going to give me 503 negative for an F net. And then F net is also equal to MA, which is also going to equal negative 503 equals 120A. Divide both sides by 120 for my acceleration. That's going to get me 4.2 equals A. So 4.2 meters per second. Okay, there we go. So in our next problem, we're going to determine the friction that is applied in this scenario. So I'm not going to erase this. I'm not going to erase all of this. I'm going to leave my variable list alone so that I can determine that. Okay, so our next problem is saying what would be the force of friction from the previous problem if the coefficient of kinetic friction was 0.15. So if I applied friction into this scenario, I know my movement is going this way, and friction is going to resist that movement. So it's going to be this way. Let's go ahead and add that to our variable list. Force of friction and the mu k. So that's going to change my F net. So let's go ahead and erase this and add in the variable of friction. Now remember, when we're dealing with this coordinate system, this force of friction is resisting the motion and it's going to the right. It's going down the ramp, and down the ramp is positive. So this force of friction has to be positive. So force of friction is equal to the negative force normal times mu k. All right, my force normal, what is that? Well, that's going to be the opposite of this Fy. So force normal equals negative Fy. I've got a negative Fy to begin with. So this negative, I'm going to have force of friction equals F in Y times mu k. So that's going to get me negative 1066 times that coefficient of 0.15. Okay, that'll give me my answer for force of friction. And that will be a negative 159.9. Okay, and that's our answer. So that's how we would find that. So I wanted to do that just to show you guys that finding the force of friction in a complex problem like this, if we added in this extra force, it really doesn't add that much work to the back end. It really just adds that extra confusion to the front end. So if you get a problem that has a lot of forces involved, which you might on our unit test, what I want you to do is go step by step. Just start by breaking out your main forces into components and making a list of those forces. It's much easier to do on a sheet of work paper than it is on a blackboard. I know, because I've been in your shoes, I've done this. Take your sheet of loose leaf paper, use each line to designate a specific variable, and then break out into your component forces, and then use those to slowly find one force at a time. We're just doing one force at a time. So if I wanted to take this and then use this force of friction, add it in to find my new resulting acceleration, that would actually be really easy because it's just F1 plus Fx plus Ff. I'm going to have, oh right, this is supposed to be positive. Sorry, forgot about that. 159.9 should be positive. So F net equals negative 1,000 plus 497 plus 159.9. Adding those together. That's going to get me an F net of 343.1. An F net equal to MA. So my 343.1 is equal to my mass of 120 times A. 43.1 divided by 120. That gets me a new resulting acceleration of 2.86 meters per second squared. So it really doesn't add that much work into finding our F net, into finding our acceleration. It just adds that extra confusion up front. So these problems weren't that hard to solve separately. Remember, we did problems where all you had to do was determine the components from the force of gravity. Then we did problems where we added an applied force. Then we did problems where we added a force of friction. So you can always break these into smaller problems, and then they actually become really manageable. Okay? So I want you guys to practice that. Practice breaking these up into smaller, bite-sized chunks. And if you need more practice, ask me. These are crazy easy to come up with. You just throw new numbers in, okay? You guys could do that yourselves. You could make problems where all you did is throw numbers in. All right? Thanks, guys.